Welcome to Section 3, Training a Supervised Learning Model. This is Lecture 8, Training a Baseline Logistic Regression Model using scikit-learn. So I've included the initial logic to load in the data frame and to pre-prepare the data, as we did in Lecture 7. We're going to be implementing the logistic regression model directly from scikit-learn. If you'd like to understand the model in more detail, please head over to this URL. This is the web page for the model specifically at scikit-learn.org. Okay, so to implement the model, I can import scikit-learn.linear model and specifically the logistic regression model. That model, I would want to initialize the model class and store that as a model variable within Python. Once I've got that model initialized, I have the ability to train the model, which I'm going to do using the training data that I partitioned in the train test split method. So I supply the X-train, which are the features that the model's going to learn on. And then the Y-train, which is the target variable, which contains the fraudulent records as yes or no, which the model will learn from and correct itself from. Okay, so let's load everything. Then once that model is trained, I have the ability to make predictions from the model by saying model.predict, and I'm going to be predicting on the test set. So that's the holdout set that I've kept aside that the model hasn't been trained on. If I were to make predictions on the same data that the model was to be trained on, that would be bad practice from a data mining or statistical perspective. There'd be a lot of bias in there. What we'd want to do is use this random holdout set that hasn't been involved in the training process at all. We evaluate the model on that in order to see how well the model generalizes on unseen data. Right, so I'm going to supply the X test, and then we can actually inspect those values to see. So what we're getting is a binary classification output where the model is just predicting ones or zeros depending on what it knows after being trained. In this case, because the data is extremely imbalanced, the model is obviously predicting a lot of zeros. The values are being truncated because it's just a massive array. There's a few thousand of them. We're not going to be able to visualize them all here, but this is just a sanity check just to show you that this is what the model's actually returning once we're running inference. Okay, so then once we've got these classifications that the model's made, the next step would be for us to evaluate the performance and the effectiveness of the classification model. So one of the ways we do that is through the confusion matrix. And the confusion matrix is essentially a cross-section between the ground truth, so the data that we know to be true, and then the predictions that the model makes. So it's a cross-section between those. And for a binary classification context, which is what we're in now, considering this is a fraud detection problem, the confusion matrix reports on the classification performance of the model by looking at 4 different quadrants or cross-sections between the ground truth or the target variable and then the predictions that the model makes. We're going to look at that in more detail now, but 3 or 4 of the concepts that we're going to look at are true negatives, where non-fraudulent data from a ground truth perspective is correctly classified as non-fraudulent by the model. So what you want to do is essentially see how many non-fraudulent transactions are predicted as such. Then false positives are the number of non-fraudulent transactions that are incorrectly classified as fraud. So our model said, these are fraudulent, but in reality, they're actually not. And there's a cost implication to that, which we will explore later as well. Then false negatives are the fraudulent cases that are incorrectly classified as being non-fraudulent. So those are the ones that are fraud, but the model never determined as being fraud. So the model effectively missed them. Then our true positives are the transactions that actually are fraud, and that the model correctly classified as fraudulent. So in this case, we're trying to obviously detect fraud. So when we speak of positives, that relates to fraud effectively, while negative refers to non-fraudulent. And true relates to correct predictions, whereas false relates to incorrect predictions. And there are a number of performance metrics for classification problems that are derived from the confusion matrix. And we will explore those in more detail in section 4. Therefore, it is foundational that we understand the confusion matrix well, and how it can explain the performance of a classification problem. So luckily within scikit-learn, we can implement the confusion matrix quite easily. So from within sklearn.metrics, we import confusion matrix, and then we can call the confusion matrix, and we then need to supply it with two arguments. The first being the ground truth for the test set. So that's the actual the labels, the true labels of the unseen data, the unseen test set. We want to effectively evaluate how well the model predicted against those ground truth variables. So the actual predictions of the model is y predict or y pred, and we always supply it in this order. So this is ground truth, and then this is the classifications that the model made. So we can run that, and then you'll see we'll get this quadrant that effectively determines false positives, true positives, etc. In a 2x2 matrix. Then we've also got this implementation here where we are making use of matplotlib and seaborn, and effectively adding some window dressing and some additional details to give you a fuller understanding or picture of what the confusion matrix looks like. We've got a legend that indicates the number of classes, or rather the magnitude of the number of records within that quadrant. But these would be our true positives. So these are cases that were predicted as fraud by the model, and the true class, or the ground truth, was fraud. So these are the fraudsters that we detected. Then these are the cases where the model missed the fraudsters effectively. So the model predicted that they were not fraudsters, but in reality they actually were. So these are the 15 that we missed. Here we've got our false positives, 6 of them, which is pretty good. Normally in fraud you end up with quite a few false positives, or that's something that we try to mitigate while trying to maximize the number of fraudulent customers or transactions that we can detect. So these are the cases where the model said, yes, it is fraud, but the ground truth says, no, it isn't. So this model does quite well from that perspective. And then the largest quadrant in terms of the number of records are the cases where the model predicts that it's normal or non-fraudulent, and the ground truth says so. So overall, this model is performing quite well. Obviously, we can improve on this. This is just a baseline solution. But as a start, that is relatively good, and it's tending to solve the problem that we're trying to solve.